This question is a maximization minimization problem from one of the review sheets. And this is a particularly difficult one, so I thought I'd show a solution to this. Basically, we have a 2-meter high wall and the beam is resting on it, and that wall is 10 meters from the building. And we want to know what is the shortest possible beam that will lean on that wall yet still touch the building. So basically, we have this situation where we have this beam, it's leaning up on a wall, and we want the shortest beam so it still touches the building over here. And I'm going to call this B. Okay, maybe I'll draw a little bit nicer picture here. We have our beam. We have our wall. And we have our building here. And we have our ground kind of here. Okay, so we want to know the shortest possible beam here. And we have a few measurements. This is 10 meters here, and this is 2 meters here. And we don't know this length, we'll call X, and we don't know this length, we'll call Y. Okay, but we know there's some similarities here. And we know that this is a similar triangle, so we know that Y to 2 is equivalent to 10 plus X over X. Okay, so the big to small comparison on the vertical side is the same as the big to small comparison on the horizontal side. Okay, so that's one relationship, but we need a relationship for B because we want to minimize the length of B. So the minimum B is, I'm going to do this. The relationship that includes those distances is going to be Pythagoras. So I'm going to say that B squared is equal to Y squared plus X plus 10 squared. And since I want to solve for B, I need to have my equation equal to B. So I'm going to square root. I'm just going to focus on the positive version of this. The other part of this is that we have too many variables to be able to maximize this. And this is where that other relationship comes in, this relationship here. And so what I'm going to do is I'm going to replace Y with 20 plus X over X. In fact, I'm going to write that as X plus 20. Sorry, 2X plus 20 over X. So I'm going to replace that in the expression here. And once I've done that, so B is equal to the square root of 2X plus 20 over X all squared. So that Y is being replaced by that, plus X plus 10 squared. Now I have an equation of B of X, so I can maximize that equation for the B value, or the length of that beam, by differentiating and making it equal to 0. Now I'm going to make the assumption that when I get a 0 derivative, that's going to give us a max, although technically that could probably give us a min. Sorry, that's going to give us a min and not a max, because this problem, really, the B is unlimited in length, because we can make a B really long and have a really shallow ramp setup that we have here. So we're looking for the minimum B, so we're going to assume that the B prime equal to 0 is going to be the minimum. So once we have this, we're going to differentiate it. This is going to be a really messy looking derivative. So it's going to be 2 square root of 2x plus 20 over x squared plus x plus 10 squared. I need to use chain rule. So this is going to end up being 2 times, and maybe I'll factor out that. I'm going to factor out the 4, the 2 squared. So I'm going to have 4. And then I'm going to have my derivative is going to give me times by 2. Write that a little bit nicer. So I have 4 bracket like that. And then the power is going to give me the times by 2. So I have x plus 10 over x times, and then now I have to apply the quotient rule. So this is just going to be 1 times x minus x plus 10 times the derivative of the denominator is x. And then I'm going to end up with squaring the denominator. Okay, so that's going to be the chain rule for that part. And then I need to also add the derivative of the next part, which is 2 times x plus 10. Okay, so that's a really ugly looking expression. However, what I can focus on is the numerator and solve for when the numerator is equal to 0. So I'm just going to simplify this a little bit. So I'm going to put the x cubed in the denominator that I have here. So I end up and factor out the 2 here. So I'm just going to first of all cancel out the 2's. I don't want to have to keep track of all these 2's. So I have a divide by 2 and times by 2 in the numerator in both the terms. So this looks like I have in the numerator, I have 4 x plus 10. The x's cancel out here, so I have times negative 10 in the numerator over x cubed plus, and I'm going to get a common denominator here, x cubed times x plus 10 over x cubed, and that's going to be all over the main denominator of square root and all that mess in there. But I'm not going to worry about that mess. Okay, so that x cubed is going to end up in the denominator. So I'm going to end up with 4x. So that's going to be, actually, sorry, multiply that out. I'm going to end up with negative 40x minus 400 plus x to the power 4 plus 10x cubed. That's going to be the numerator. And in the denominator, that x cubed is going to go down, and I have that big, gigantic mess here. Okay, so since I'm making this equal to 0, I'm just going to focus on the numerator equal to 0. Okay, so this means that I can solve the equation x4 plus 10x cubed minus 40x minus 400 equal to 0. Now, this is not factorable. I don't have whole numbers, so I'm going to have to graph this. And in graphing this, I have 2 solutions, but the only positive solution I get from graphing this is going to be 3.42. Okay, so that gives me the x value that maximizes the length of the beam. Well, I don't want the x, I want the actual length of the beam. So I'm just going to plug that back into my b equation. So b of 3.42, when I plug that in, I plug that into the original equation up here. And this is still kind of a gigantic mess here, but I'm going to plug in my 3.42 for x plus 20 over 3.42, and then I'm going to square that all, plus 3.42 plus 10 all squared and square rooting that, and that is going to give me the value of 15.8. what's that value again? 15.55. Approximately. Okay, so what that means then is that the minimum length of that beam for this beam to reach that the wall, over top of that little wall of 2 meters is going to be about 15.55 meters is going to give me the minimum length. Okay, and again, we're going to assume that's the minimum because really we can make this length as long as we want by just kind of stretching it out and making it more and more horizontal. That would actually give us there's essentially no maximum to this value. So this is our minimum value length. Okay, so this is a particularly difficult problem of maximization, minimization. Okay, but the main idea is we need to set up the variables. We need to then write an equation for the b value that we want to minimize. Okay, in this case, we made it in terms of x's and y's. We can't have two variables, so we need to find this other relationship that I've highlighted in black that relates the x and the y's. That allows us to substitute for one of the variables, and which gives us the equation, and this is a key one right here. Oops. This is a key one right here. This is an expression that we are able to differentiate to get our slope of 0 to maximize the b value.